Next, we're going to talk about probability distributions for continuous random variables. We've been talking about probability distributions for discrete random variables, where there was essentially a fixed number of possible items that or values that a particular random variable can take on. Here, for a continuous random variable, there are an infinite number of possible values, and essentially you're just limited by how precise your measurement can be. So, for example, a continuous random variable, let me get my red pen. A continuous random variable would be, let's say, the miles per gallon a car gets for its gas consumption. It could be 32, it could be 32.11, it could be 32.1111, it could be 32 point, and I think you get the idea. There are infinite number of possible values. We could talk about also the distance for a field goal in football, 30 yards, 31 yards. Typically, that's the way that one hears distance talked about, but in fact, it could be 30.5 yards, 30.25 yards, 30.367589 yards. Again, an infinite number of possibilities. And so, in many real-life situations, we actually measure continuous random variables versus discrete random variables. Now we want to talk about how we can deal with quantifying probabilities in the population associated with these kinds of random variables. It is very important to note that while a lot of the concepts here will be the same as what we saw with discrete random variables, there are some very important differences. So let's go back to this old GPA probability distribution example. Let's let y be a random variable representing GPAs of students on campus. And suppose the probability distribution for the random variable y is denoted as what I have here. So we are no longer for, well, let me back up. So for discrete random variables, we would often see something like this, where we use probability y is equal to little y. We are not going to be able to use that anymore, and you'll see why coming up. Instead, we write things in terms of a mathematical function. So in an algebra class, you've learned that you have a function of x, or f of x is equal to maybe 2 plus 3 times x. Well, that's what essentially I've represented here as the probability distribution for y. F of y is equal to 15 divided by 2048 times y to the fourth power times 4 minus y. And this is for GPAs between 0 and 4. So we're dealing with college GPAs here. Now for all other possible values of y outside this range, f of y is going to be 0. Okay. Let's take a look at a plot then of this probability distribution. So to do the plot, I'm going to use a function in R called curve, a very, very useful function. And to give you an idea of how it works, let's say I wanted to plot f of x is equal to x squared. Okay, the way that I would do that with the curve function is I say curve, and then the first argument is expr for expression. And next I put, well, what's on the right-hand side of that equation? X squared. And let me also give some limits for where I want to draw or evaluate f of x at. Let's say x lim is equal to, I'm going to combine negative, let's say 2 to positive 3. And if we run that, we get the plot, again, to a different monitor. And here we go. If I wanted to make that a red color instead for the function, well, then I have available to me, the same kinds of arguments that we had in the plot function. And there we go. So there's the nice little function there. Let's talk about now how we can plot then the corresponding probability distribution for these GPAs here. Okay. So again, I'm going to use EXPR. 15 divided by 2048 times, and R requires that you always write this in terms of x. So in other words, we're saying, well, what values go on the x-axis? And while we're dealing with a letter called y, well, it's still going to mean the same thing to us. It's going on the x-axis. times 4 minus x. And I want to draw this between 0 and 4 because, again, that's our limits. Color is going to be red. I'm going to put a title on my plot, y-axis label, x-axis label. And note that this f of y is equal to 0 for all other possible values of y. Also, I will tell you, if we take a look at this right here, this f of y is always going to be greater than or equal to 0. So because of that, I'm going to put like a little border on my plot where I'm going to draw a line on the y-axis at 0. And the way I can do that is with the AB line function with the h argument for horizontal line. So I'm going to go ahead and do that. Take a look at the plot. So here's our probability distribution. Obviously, it looks different from what we saw like with the binomial distribution because now we have a continuous function that we're working with. But what this function is representing to us from 0 to 4 for values of y, areas underneath that curve all the way down to on the y-axis equal to 0 represent probability. So for example, if I want to know what's the probability of having a GPA between 2 and 3, all I would need to do is find the area underneath this curve in this region that I'm coloring in. If I wanted to instead, let's say, find the probability that a GPA was greater than 3.5. Well, here's about 3.5. I draw up, and again, the area underneath the curve all the way down to 0 represents probability. Okay. So what exactly did this function here represent? This f of y basically is what I'm plotting on the y-axis. So for example, if y was equal to 2, I just simply plug in 2 for y here. If you see where my mouse is, 2 for y here. And I would get, approximately about 0.21, 0.22. Now, I guess in this example I did 3 instead. This height of the curve is not the same as the probability y is equal to 3. It's not the same. So again, when we were dealing with discrete random variables, we would have on the left side of our equation probability capital Y is equal to small y is equal to, and then there's our function. Here with continuous random variables, the same doesn't occur. And we'll come back to why that occurs later. But still, the area underneath the curve, that's what corresponds to probabilities. So for example, let me erase this again. If I wanted to find the probability that y is between 2.5 and 3.5, I would want to find this area. Now, many of you have had a calculus class. How would you find the area underneath the curve in that kind of a situation? Well, simply integrate. So you would take, you would integrate from 2.5 to 3.5. My function, and we're going to put a dy there because we're integrating with respect to y. If you go through all the calculations, you get 0.5593. Let's go back to this plot. Well, I didn't necessarily draw that area very well, and I think we can agree that, roughly speaking, about half the area underneath that curve I've colored in with my pen. Now, unfortunately, not all students in our class have had a calculus course, so we're not going to focus on calculus here. I will periodically still show you how to do the calculus because I know a large number of you have had a calculus course, but I won't ever require you to actually do an integration, for example. If you do want to know more about the approach to statistics that does use calculus, take a mathematical statistics course. Now, the reason why we don't need to actually use calculus in our course is because R has nice functions that will essentially do the calculus for us. It will find the area underneath that curve. Now, let's take a look at some questions here. Suppose the interval that we were trying to find as the area underneath the curve was small. Let's say it's 2.9 is less than y is equal to 3.1. Let's go back to this plot. Is that probability going to be smaller or larger when we did probability of 2.5 to 3.5? Of course, it's going to be smaller. I mean, we can see it on that area here. So let's go ahead and do that. Let's actually draw it, and I'll do my best to try to draw it correctly. That didn't work out very well. Oh well. And here we go. Obviously, that area is a lot smaller. Now, what would happen though if I try to make this interval that I'm looking at even smaller? Let's say instead we're at the probability of 2.99 is less than y is less than 3.01. Well, again, you would expect then that corresponding probability to be smaller than when it was up here. And we could keep on going, making that interval even smaller. And eventually, that probability is going to be so small, eventually you're going to get as close to 0 as possible. And so that's why you cannot necessarily just find for a continuous random variable probability y is equal to 3. In other words, probability that your random variable is equal to one particular number. Now, for those of you who've had a calculus class, you know that if I were to take that expression for f of y and integrate from 3 to 3 of f of y dy, of course, that would be 0. So it's more of a, I guess, a calculus explanation of this. So let's take a look at another example. This is dealing with wind speeds again. And wind speeds are often characterized by probability distributions. And the reason why utility companies would want to do that is so that they have an idea of how the wind speeds are distributed in the population of all wind speeds, and they can make judgments then about how much energy that a wind turbine could actually generate based upon what the expected wind speeds would be. And so for Lincoln, here is an actual probability distribution that one could use that does characterize wind speeds rather well in our data set. This probability distribution has a name. It's called a Weibull distribution. And similar to what we saw with the discrete random variables, there are a number of probability distributions for continuous random variables that are quite useful, and they have names associated with them. This is one particular one. And unfortunately, I left off some stuff right here. Gamma, as in the Greek letter gamma, the Greek letter delta, and beta in this expression are all parameters. They're actually population parameters. And in a real-life situation, we would actually want to estimate them. I actually did estimate them using a technique called maximum likelihood estimation. Don't worry about that in our course. And what this gives me is what those particular parameters would be corresponding to, or those are the best estimates of those parameters given my sample. Well, let's actually look at a plot then of this probability distribution relative to our histogram. So in the previous section, we did a histogram of all the wind speeds. And all I did in this particular plot is I plotted that histogram and I adjusted the y-axis. And don't worry about how I actually do it. I adjusted the y-axis so I can also get a plot of this probability distribution on it. And as you can see, this probability distribution generally follows the same shape as that histogram. And so what this is telling me is in that since this sample can be characterized by this probability distribution in a decent manner, why not we just use this probability distribution then for all wind speeds that are in our population itself? And that's what's actually done in the real world. So then how could we use this then? Well, we might be interested in, let's say in order to actually generate energy from the wind turbine, maybe I need to have my wind speeds to be at least 8. And if I come up here, I could look at, well, how often will this wind turbine not be generating energy? In the reverse way, how often will it be generating energy? That's how these probability distributions are used for wind generation. I'm sorry, for not wind generation, but electricity generation from wind turbines. So here are some general characteristics of these probability distributions for continuous random variables. Again, we will always denote it as something like f of y. For other situations, I might use, let's say, f of t, where my random variable itself is a capital T, or maybe I could say g of y for a random variable y. There's no special reason why I'm using f of y. So f of y is always going to be greater than or equal to 0. F of y itself can actually be greater than 1. Now you might be thinking, wait a second, probabilities can't be greater than 1. No, they can't. But remember, probabilities are area underneath that curve. So you could have a particular probability distribution such that f of y goes above 1, but still that area underneath the curve is equal to 1. And we'll see examples of that throughout the semester. Now, the integral over y of f of y dy has to be equal to 1. And this corresponds to that all probabilities sum up to 1 for a corresponding random variable, similar to what we had with the discrete random variable case. Now, very often, you will hear these probability distributions, often referred to as probability density functions, when we're dealing with a continuous random variable. But what about expected values? We saw these with discrete random variables. Could we do expected values here? Well, yes, we can. So I might be interested in, well, what would I expect the wind speeds to be on average? And so I can find the expected value of y for that. And if you can go ahead and do the integration over the range that y is, perhaps it's between negative infinity and positive infinity. And the GPA example would be between 0 and 4. And what you do is you take y times f of y of dy. That would be the integral that you would actually do. Again, don't worry about the integration in our particular class. But instead, if you haven't seen calculus, or even if you have seen calculus, you can see how this equates to what we had with discrete random variables, where we would take the sum of y times the probability that large Y is equal to little y. That integral acts as the sum. The f of y acts as the probability of a random variable y is equal to some value. And again, we would typically call the expected value of y equal to mu. It's our population mean. One could also look at a variance as well. Remember that a variance is found from the expected value of y minus mu squared. Now we are integrating again, but now we have a different term that we're multiplying f of y by. Again, we could also refer to this as sigma squared 2 and also the variance of y. So that's a quick little introduction to probability distributions for continuous random variables.